Okay, so hello everyone, good afternoon. My name is Sophie. I'm a materials engineer from Austria originally, and I'm an academic at the University of New South Wales in Sydney. So just to begin with, what I do in my day job, I lead a research group of around 20 early career researchers, so that's postdocs, PhD students, and undergrads, and we are interested in, firstly, next generation aerospace materials, but more recently we also got into the quite exciting area of metal additive manufacturing. So my research is funded roughly 50-50 by collaborations with national and international industrial partners, sometimes also by the Australian Research Council linkage scheme. However, in the last 4 years or so, the real game changer for my group has been funding by the so-called OSMURI project, which is supported by DST, so more on that later, and that's how we got into metal AM, and which I sort of regard as the future way to go for Australia. We have access to amazing facilities for processing, characterization, testing, and modeling of alloys, and the alloys that my team is interested in for aerospace are nickel-based superalloys, titanium alloys, and then several advanced steels. So a lot of the motivation for my research, and that actually ties nicely into the previous talk, is that there's a lot of air travel. I mean, obviously it's been a bit disrupted by the global pandemic, but still there's forecasts, for example, this one here by Airbus, which predicts around 39,000 new aircrafts within 25 years. And what's even more important is that all of these aircrafts will have next generation aircraft engines, so different technology. So taking into account that a lot of climate change is due to air traffic, so one way how we can improve this situation is to reduce, obviously, particulate emissions, fuel consumption, and what's good for the passengers, obviously, is reduced travel time and airfares as well. And one very important means to do that is related to improving the engine efficiency, and that ties closely to materials engineering. So let's have a look at an aircraft engine. An aircraft engine has a bunch of different parts. However, we are often interested in the high pressure turbine and low pressure turbine. And here a higher temperature, faster rotation, and higher load translates right into better efficiency. So the part that my research has been focused on for probably a decade or so is the so-called turbine disc. That's this part here that carries the so-called fan plates. And in order to increase the efficiency of the aircraft engines, we want to have high temperatures, so ideally above 650 degrees C. There's high mechanical loads, fast rotation, and then there's very harsh environments, so fatigue, creep, corrosion, oxidation, and all that. And therefore, we need so-called nickel-based superalloys to build these parts. So in order to make better turbine discs, we need to understand the interrelationships in materials engineering. So what we want is obviously better performance and better properties. We can tweak the processing to achieve that, but the really kind of missing link between all of those is microstructure, and that's what my team and I are pretty good at. So let's look at how we can make modern aircraft engine parts. So there's obviously conventional routes. So this is a photo from an industrial partner based in Europe. So it's actually massively complicated, and conventionally processing requires large plants. So you need to cast these materials, you need to remelt them often 3 times, you need to undergo a complicated multi-step forging procedure at high temperatures, and at the end you need to apply a thermal treatment to get amazing properties. However, nowadays there's obviously new ways of doing that via metal additive manufacturing, and my team is here very often interested in powder bed fusion, so more on that later. But what we are ultimately wanting to achieve is to shift these curves to higher temperatures and higher strength. And you can do so by, getting the best out of existing materials and by designing new materials. So this is an example from my research on alloy 718, where we work a lot on a forging schedule that's called DA, or direct aging, that achieves the highest strength properties. The key for all of that, as I said, is microstructure characterization, and we do a lot of microscopy. And I mean, don't worry about the details here. What I just want to show with this slide is that we need a bunch of correlative techniques, and they range across several length scales, because these microstructures are highly hierarchical, and that's how we achieve amazing properties. So we can use light to, on the left-hand side here, show grain and dendritic structures. We can use electrons to sort of go to the micrometer towards the nanometer scale. We can extract crystallography information. We can extract information in 3D. And another quite important tool for my research is the so-called atom probe, where at the nanoscale we can image individual atoms and understand the nanoscale chemistry and morphology. So let's apply that to an example from conventional processing. So what you can see here is the slice of a real-world forged turbine disk made out of Inconel 718, and it's overlaid by a hardness map. You can see there's vast differences because these parts are actually really complicated, and what we don't want to have, so this is kind of a worst-case scenario map here, in this blue region D, we achieve a way lower hardness than in the other regions. So what my industry partners and I do is a lot of modeling, so we can find out things such as temperature, strain rates, strain, recrystallization, thermal profiles, etc. But all of that is not enough to create a real digital twin of these turbine disks and the different positions. So let's just quickly dive into the microstructure here. So what we did here is we characterized a bunch of interesting regions. I mainly want you to focus on this region D here, which is the one with the kind of worst case properties. So what we can see on the micrometer scale here on the left, you can see individual crystallites, so individual grains. That's how this material is made up on the micrometer scale. And we can see that in this region D, the grain size is much larger. Another example is shown here. So what we're interested in is having a slightly higher volume fraction of these white particles than we can see here in this region D. That's the so-called delta phase. It's very important to pin grain boundaries during processing, and it's also an important source for niobium that we need in the next step. So in the next step, here you can see some atom probe microscopy, so that's real nanoscale information of forged positions from this disk. And what you can see here is a slight decoration of the microstructure with nanoscale particles. So there's two kinds in this alloy. One are called gamma double prime precipitates, they're rich in niobium, and the other ones are called gamma prime, the turquoise ones. So after forging, there's only a little bit happening. The good news is the direct aging process is really robust, and if we subject these disks to a final thermal treatment, we achieve what we want to have, a very kind of dense and interconnected nanoscale decoration with precipitates. So that's all very nice, but why is this useful? So my industry partners can create digital twins where we can very accurately predict all the various strengthening contributions. So don't worry about the details here, but there's many, and that's related to the microstructure, and we can do this for all these different positions, and then create turbine disks with better properties. So I want to jump on to another quick example for sort of really aerospace. So this is a material Rene 41 that's also being manufactured in Australia, in Perth. It's actually an old alloy. It's been to outer space, which is pretty cool. So Project Mercury, these capsules, they had Rene 41 shingles to protect during re-entry. And this is one of the most highly alloyed and strongest nickel-based superalloys, and it's crazy interesting for next generation aircraft engines. However, it's not easy to manufacture, and if you get it wrong, this happens, and this is going to go back to the scrapyard, and that's going to be huge losses for the industry partners. So what we do in my research is we do modeling, so we can predict precipitation of secondary phases as a function of the alloying contents. We can underpin this by microscopy. And with that, we can define sort of safe processing conditions for my industry partners to make better Rene 41 parts. I now want to jump on to what I believe is maybe the future for an Australian manufacturing of aerospace alloys that's independent of supply chains and more resilient. So this is related to metal additive manufacturing. And I want to just shout out to the so-called OSMURI funding. Our project, don't worry about the complicated name here, it's on metal additive manufacturing. It's in its 4th year. I collaborate with a team from the University of Sydney, so we are very good friends in this. So Professor Simon Ringer and Professor Xiaozhu Liao. And we are also connected with 6 universities from the United States. And this is led by Professor Suresh Babu at Tennessee Knoxville, who has strong linkages to Oak Ridge. So metal additive manufacturing is really kind of a disruption and a new way of doing materials engineering. So rather than, casting and remelting and forging big blocks, all of it starts with metal powders. And these metal powders, the powder beds, as you can see here, they can be molten layer by layer by using electron or laser beams. And then we can create 3D objects that are very complex and intricate. This is at the same time also a little bit of an advertisement for my colleagues at the University of Sydney. They have recently launched a new Sydney manufacturing hub where we can 3D print titanium alloys, steels, and nickel-based superalloys using electrons and lasers, and they can also 3D print ceramics and all sorts of exciting stuff. So just coming briefly back to the Inconel 718 example, that's what we've seen before, the turbine disc. I'm not going to go into too much detail, but rather than playing with the forging in 3D additive manufacturing, we can play with the scanning strategy of the laser beam in this case. So you can see here a chessboard pattern, and at the bottom you can see a linear pattern, and again you can create vastly hierarchical and different microstructures. I'm not going to go into any detail here, but we again need to study them across several length scales to understand how we can achieve better properties. We can also subject them to thermal treatments to achieve the same kind of nanoscale structure of gamma prime and gamma double prime particles, and we can use that to put into models and predict better properties. Last quick example, this is for electron powder bed fusion, and we are very excited about that because the electron beam allows us to do very different and new scanning strategies. So in this case, we used a so-called random scan generator, which just fills random points. And this enabled us to print a traditionally non-weldable nickel-based superalloy, Inconel 738, crack-free. So you just got to believe me that based on these micrographs here. And at the same time, without doing any additional thermal treatment, because this is done at slightly elevated powder bed temperatures, we achieved a nanoscale in situ precipitation of particles that we wanted to have. So to sum up, microstructure and materials engineering, so what it will enable us to ultimately create better aerospace parts with superior mechanical properties. I can maybe relate that to the example from yesterday, the spear, if you remember that. So what my team can do is provide the perfect material for the spearhead, right? And this is how it fits into the larger scale of things. We can also provide input data for modeling. We can develop strategies for the design and processing of new classes of alloys for next generation aerospace applications. And additive is a big game changer and will allow us to do things very differently, and that's very important for Australia, I think. So I guess my message here is additive manufacturing is the new way of doing materials engineering. And to sum up, I'm here to sort of, explore new ways of collaborations and what's next maybe after my OSMURI project. So if you think that we can help each other in any way, so please feel free to reach out to me or my colleagues at the University of Sydney. While we're taking questions, I just want to play a video in the background. It's just fancy pictures, no words. It's about the new Sydney Manufacturing Hub to just get an idea how excited we are about that. So I hope this is playing. Maybe, oh, okay, we can turn down the volume. So.
Thank you very much. All right, questions? Questions from the room? Yeah.
So again, me, sorry. If I was Mike Trout from Germany, if I was the CEO of Airbus, I would immediately engage you.
Oh, thank you.
Yeah, as soon as you can tell me that it's going to be cost effective. So how far are you from, with your research, from being, let's say, a good competitive level to normal production?
Are you talking about the additive part or the first half of the presentation? All of what I've shown that is actually real materials that go into real aircraft engines, so it is cost effective. And to give you one example, this so-called direct aging process that we use is actually more cost effective than previous processes that were used, because it skips a very important, previously very important 1100 degree heat treatment. So we just skip that altogether, making it shorter and saving energy. And at the same time, we gain roughly plus 10% in high temperature strength. So definitely cost effective if these numbers help. The René 41 materials, the problem there is the yield. They sometimes tend to crack because they're so highly alloyed. But we have helped our industry partners there to, within the specification, adjust the chemistry, and we have largely mitigated these issues now. I hope that helps.
Yeah, of course. So it's going to be...
I'm not so good with the cash numbers. That's the job of my industry partners.
That was exactly my question.
Okay.
Okay, thank you.
No worries.
Any more questions before we move on? All right, if not, then let's thank our speaker.
Thank you.